Thanks, Carrie, and thanks, John, for organizing this, and thanks, Alan, for also all the work that you're doing at the state level to address these issues. I'm going to be talking about some measurements that we've made on the TRAX. We put some instruments on top of a TRAX train, and some really interesting things that we're finding from that research project. So, Alan mentioned this briefly, but nitrogen oxides are an important component of the air quality issues that we have. When I'm talking about NOx, it's NO2 and NO, of course, and NO2 is a criteria pollutant, and it also contributes to the particulate matter that we have in the pollution or in the wintertime. NOx combines with ozone and other oxidants and aerosols, and it eventually contributes to ammonium nitrate. And then in the Salt Lake Valley, it's been estimated that about 70% of the PM2.5 comes from this secondary aerosols produced through these chemical reactions. So the TRAX train, you can see we put some instruments on top of a box, on top of one or two TRAX trains now, and we have this box and we've just packed it full of instruments here. Got it started in 2014, and we measure greenhouse gases and pollutants, and all of the data is posted in real time on the web. So if you go to our website, you can actually see the real-time data and see the varying levels of all the things we measure in real time. And today I'm going to be talking about, we had about a year's worth of NO2 measurements on the TRAX trains. We got the instrument, actually it was borrowed from the equipment manufacturer, and so we were able to borrow it for a full year, and so we have a full year of measurements. Just to give a little more introduction of TRAX, so this is the TRAX network throughout the Salt Lake Valley. Our instruments are on a train that travels on the green and red lines, so we have all of our data comes from the green and the red train lines, and they provide really nice coverage across the Salt Lake Valley. And before I jump into the NO2 results, I just wanted to talk about some of the other measurements that we've made in the past, and I've talked about this before, so this may be a review for some of you, but I just wanted to make sure to mention it. So this is an annual average of CO2 measurements that we made, and you can see kind of the broad spatial features for CO2, that it's lower outside of the city, and it's more elevated along the urban corridor. And you can also go through and look at every single road, you see a little bit higher CO2, and that's because of the vehicle emissions. That's exactly what you'd expect, but it's really neat to be able to see these features in actual real measurements. We also measure methane on the train, and again, this is an annual average, and the spatial pattern is very different for methane. It's really dominated by these individual point sources, and those are associated with commercial and industrial facilities that we know potentially have released methane. We also measure ozone, and so here is a summertime average through the summer of, I think it was 2015, and the spatial patterns are just the opposite of CO2. It's higher on the edges of the city, and it's lower in the urban corridor, and we'll talk about more about why that is in just a few minutes. And then we also have PM2.5 measurements on the train as well, and we've been looking at the PM2.5 data a lot recently, looking at the different spatial patterns that exist throughout the valley during inversions, and this is what you see up there is just one pattern that we see that's pretty common, but there are different spatial patterns. Sometimes it's higher in the south or the north part of the valley. And so understanding how the pollution moves around during different meteorologic conditions is really important. Understanding thermally driven circulations and terrain-driven circulations, all of this affects the data and the air quality in different parts of the city, and we're able to see this with this measurement platform. But today we're going to talk about NO2 primarily, and so this is the annual average of the NO2 data that we measured for that year that we had that instrument. And again, you see that it's elevated along the urban corridor, and it's lower along the edges of the city, and that should sound familiar by now. If you go and look at the relationships between NO2 and CO2, they're actually quite strong, and it's because they're co-emitted during fossil fuel combustion. If you just take the correlation coefficient between the NO2 and the CO2 data, it's actually 0.83. So it's a pretty good correlation between the two of them if you just look at the averages. NO2 is also related to ozone through photochemistry, atmospheric chemistry, and if you look at the correlation between those two, it's even stronger, negative 0.96. They're inversely correlated. And to me, one of the things that this kind of a side point is this really illustrates the complex signature and interactions from fossil fuel combustion, that how it affects urban air quality in a number of different species. It's not just one factor. So in order to understand the different sources of NO2, one of the tools that we can use to look at is the ratio between NO2 and CO2. They're co-emitted, but different emission sources will have different levels of emissions of one species versus the other. So by looking at the ratio, and I'm actually going to be looking at the excess ratio, so you subtract out an estimate of the background and then just look at the ratio of the two species. And that's plotted here in the bottom. You can see that there's a really large feature in the center of the valley, and that's drew our attention. And what the heck is that? And what's driving that is that there's really high NO2 here in the center of the valley, and there's not high CO2 associated with it. So that kind of drew our attention, and so that's what we're going to be looking at. This is a different way of plotting the data. This is just an XY plot looking at it's the same data that was plotted in the Google Earth plots, but it's just a different way of looking at it. And you see the ozone at top, NO2 in the middle, then CO2, and then here's this ratio at the bottom. And if you want to, you can squint and look, and where this green shading is. And sorry, this is the TRAX red line and the green line. It starts from north and goes south. So this is up by the university, and this is down by Daybreak. On the green line, this is out by the airport, and this is in West Valley. And so the green shading is where the TRAX red and the green lines overlap. And if you look, you can start to see actually how these features on both the green and the red line, even the really small features match up between the two lines. And the reason why that is the terrain is either on the red or the green line. They're independent data sets. But once you average a bunch of data, even the small features you see are really significant and are a function of the different emission sources and sinks in those areas. So that gives us confidence that what we're seeing is a really consistent signal. These yellow shaded regions are areas of interest. This first one is where in 400 and 500 South, where the train is in the middle of traffic, and I'm not going to talk about that one today. But this B and C are both areas where TRAX crosses I-15. This is in the southern part of the valley, and this is on the green line out where it's going out towards the airport. And something that I'll note to put in the back of your mind is in both spots where the train crosses I-15, see about a 3 parts per billion kind of bump of NO2. And so I'm just going to ask you to keep that in the back of your mind. And then the next few slides, I'm going to be talking about this really big feature over here where we have this large feature in NO2. So this is just blowing up that last section. And we see that, and now this is looking to the north. So in the NO2, there's actually that big spike actually has two distinct peaks on it. And when you look at NO2, one of them is centered over the freeway, and then the other one is centered just really right adjacent to the freeway. And then when you look at CO2, you can see the CO2 feature is really only centered on the freeway, and you don't see anything over here. And then, but if you look at the ratio is really centered over this secondary bump in NO2 over here. And what's going on here is that there's a proportional increase. So at the freeway, there's a proportional increase of NO2 and CO2 at the same time. And so it doesn't cause a bump in the ratio. But in this spot, there's much greater NO2 emissions relative to CO2. And so it's creating this pretty large feature, which is defined by this ratio, and it has a pretty wide spatial extent. And so what you're seeing is the NOx emissions from the freeway superimposed on top of this bump that's from this other source. And I mentioned the 3 part per billion bump where the train crosses the freeway. If you look at the magnitude of this small bump that's superimposed on this larger feature, it's about that same magnitude. So we're seeing a consistent elevation from freeway emissions in NO2, and it's just being superimposed on top of this much larger NO2 feature right here. So here's all these different species plotted together, and I've added ozone on the top. You can see ozone is just a mirror image of the NO2. And you can see all of these things in how well they line up. And this is where I was going to talk about. So yeah, so there's this about 3 parts per billion bump of NO2 there. We can also look at the spatial extent that we can see this feature along the TRAX line. So just looking, and this is a plot of the ratio throughout the valley, and you can see that it's slightly elevated for about 3.5 miles along the red line. And so, and this, again, this is an annual average, so this is the average conditions that we're seeing this feature. During different wind conditions from day to day, if the wind is blowing north or south, you'll see this plume move to different areas of the valley, and it goes much further than this, but on average, we're seeing these elevated values about 3.5 kilometers or 3.5 miles around this area. So what's going on here is this is the Union Pacific rail yard, and there's switcher locomotives, and we've been talking about that. There's been a number of conversations about that so far recently. They're diesel locomotives. They're often very old. They run for a really long time. They're really important for the economy because they perform an essential function. They move rail cars around within the rail yard, and there's a lot of commerce that comes in and out of the valley on the rail yard. So they perform a really important function. They often operate 24/7, 7 days a week, and one of the reasons is that they're really big diesel engines and they're difficult to start up. Also, in the wintertime, they use water. My understanding is they use water to cool their engines, so you can't let it freeze because that would destroy the engine block. And Glade at DAQ has done an analysis of the switchers in Utah, and he's found that there's 60 switchers in Utah, 49 of which are run by Union Pacific. And of those, 30% are Tier 0 and 70% are Tier 0 plus. So these are really old technology. They're just old diesel engines. Replacing the Tier 0 plus with a Tier 4, a modern Tier 4 engine, would reduce the NOx emissions by close to 90%. So a really big improvement in air quality. Glade has also looked at the cost effectiveness of this and found that the cost, about $3,500 per ton, is well within the Utah Air Quality Board's level of cost that they're willing to allocate for improving area sources, and well below that of large point sources, if you consider the railroad as a point source. But states are prohibited from establishing emission standards for locomotives, but you can do things like incentives programs or MOUs. And there was a bill in the state legislature to help out with this year, and I don't think it was passed, but it may come up again in the future. But the point that I want to make is that with these TRAX-based measurements, we're going to be able to see, if those improvements in emission technology happen, we'll be able to monitor this and see the improvements in air quality kind of in real time as they get deployed. So we'll be able to know how much the air quality was improved as these things get deployed. So some take-home points. We've used this TRAX platform, and we've got a whole bunch of measurements, and there's a lot of science that we can do with this. We're really just digging into these data sets and trying to get them out to all of you as well. So we want to have as many collaborators as possible because it's a really rich data set. This multi-species analysis can help us identify sources, and such as the switcher locomotives, some future directions. As I mentioned, this NO2 analyzer was a loaner from the equipment manufacturer, so we're looking for ways to get a new NO2 analyzer so that we can have these measurements going on in the future and get NO measurements so we can understand the full NOx budget. One one important thing to understand that we'll be looking at in the future is looking at day versus nighttime measurements, because the daytime versus nighttime chemistry for NOx is very different, and that might help us understand the overall NOx budget and contributions to air quality. And also integrating all of these measurements into atmospheric chemical transport models will really help us understand the overall budget. So with that, I'd really like to thank TRAX. They've been really fantastic in hosting our instruments, and funders that have helped us put together this research so far. And so with that, I'll take any questions. Thanks.